This is video 1 for our lecture video series from Wednesday, March 15th, where we are going to do a warm-up here. So let's look at this warm-up question. So example, do you expect helium-2 or diatomic helium to be a stable molecule? Use molecular orbital theory to justify. So anytime that you are asked to predict whether a molecule is stable using molecular orbital theory, what this means is we need to calculate bond order. Because if we have a bond order of 0, then that means that we don't form any kind of bond between these two atoms. Likewise, if we've got things like bond orders that is less than 1, that means that we are weakly stable, right? We still have some kind of bonding interaction due to electrons being filled in some partial way in molecular orbitals. But typically when looking at small bond orders like 1 or 0, we would say that these are not necessarily stable molecules. So if we are going to get bond order, then we need to first find our molecular orbital diagram. So let's go ahead and draw our energy axis. Let's place our two atoms to be bonded together to the left and to the right, and then the molecule to be made in the center between them. And I again like to write my electron configuration underneath each of my atoms, just so that I'm super clear about what is going to be coming together in our combinations to form our molecular orbitals. So helium, this has an electron configuration 1s2. So I'm going to be looking at the combination of these s orbitals. So the linear combination of atomic orbitals for my s orbitals. Okay, I'm going to draw a line, or you know what, I think I'm going to switch to boxes now, just because my lines and my dashed lines in these diagrams are not necessarily super clear. So here's my 1s and my 1s from each of my helium atoms. And then when I think about the combination of my s orbitals, again, I have my additive or constructive combination that is head-on, that is going to form a sigma sub s. So if I've got a 1s here and a 1s here, then my sigma sub s will be here. This is a lower energy, more stable bonding orbital. And then higher in energy, I'm going to have my sigma s star, or my anti-bonding orbital. This looks like this-ish, where I have one planar node. Okay, and I'm going to use dashed lines to show what atomic orbitals are responsible for the formation of these molecular orbitals. So I'm showing here that it is the constructive addition that gives me my sigma s, and my destructive addition that gives me my sigma s antibonding. And now I need to fill in with my electrons. So each helium atom has 1, 2 total electrons. So I'm now going to fill in these 4 electrons into my orbitals, working from lowest energy to high. So I'm going to first fill 1, 2 electrons into my sigma s bonding orbital, and then 3, 4 into my sigma s star anti-bonding orbital. So now let's calculate bond order. And remember, bond order is 1/2 times the number of electrons in a bonding MO, EMO, minus the number of electrons in an antibonding molecular orbital, ABMO. These are acronyms that I have made up. All right, let's see if we can't find the number of electrons that are in our bonding molecular orbitals. So of our molecular orbitals that have been made, we have only made 2 because we've only looked at the 1s atomic orbitals combinations. And of these 2, only one of them is bonding. That is our sigma s. And inside the sigma s bonding orbital, we have 2 electrons that are housed. Okay, number of electrons in my antibonding orbitals. Again, I've only got 1 antibonding orbital here. That is my sigma s star. This is also my highest occupied molecular orbital. It's the highest energy orbital that is occupied or contains electrons. Okay, so in that sigma s star, I've got 2 electrons. So 1/2 times 0 is 0. So my bond order is 0, meaning that there is no bond that is formed between each helium atom in this diatomic helium situation. And this feels right because, as we know, if I were to draw a Lewis dot structure of helium diatomic, I would have 4 total electrons. So I would use 2 to connect, and then I would have 3, 4. And this disobeys my duet rule. So this is not a particularly stable molecule or a molecule we would expect to find as a result of, as a result of the bond order that we've calculated. And this also agrees with Lewis. Now, one thing to note is you will be asked in your homework and on future assessments to predict the stability of polyatomic ions. And just like we did in our Lewis dot structures, if it is an anion, you're going to add electrons after filling your regular electrons in your molecular orbitals. And if it is a cation, you're going to remove electrons after filling your regular electrons, and you're going to remove from the HOMO first. So we're always going to remove from the high energy or less stable molecular orbital. All right, so anytime you're asked to predict the stability of particularly here little simple diatomic molecules, you will be using bond order to make such assessments. So that was our warm-up. And let's now talk about this notion of SP mixing in video 2, which is where the overall structure of our MO diagram deviates a little bit from what we've seen so far for our homonuclear diatomics like oxygen, fluorine, and diatomic neon. So I will see you coming up in video number 2.